So in this video, we're going to go over the first part of the exam review, which is actually our homework 2. So this is all the concept from lecture 1, Intro to Computing for Engineers. If you remember, we had quite a bit of modules, one of the modules rather in lecture 1 kind of introduced the basic architecture of the modern digital computer and the majority of the computers that we use now. Remember that a computer is anything that satisfies the von Neumann architecture. It's not necessarily a laptop or a desktop. It's anything with memory, processing, and I/O. But particularly all of those digital computer systems, maybe it won't be that way in the future when we move to analog, but for now, everything is storing information in the binary or base 2 number system. So hopefully everyone had that down. And you had a little bit of foreshadowing that that is in fact the answer, because here in problem 2, you actually have a binary number. How do we know it's binary? Well, first and foremost, each of the digits is either 0 or 1. That is the correct kind of digit alphabet for a binary number. And in addition, since the digits 0 or 1 are also included within the library of the actual decimal number system that we typically use, we denote that this is a binary number with the subscript 2. So in order, assuming that this code corresponds to an unsigned integer, the way that we would convert to decimal is to do a place value expansion, starting with this bit. Remember that bit is a word corresponding to a digit in binary, all the way to the right. And remember that this bit all the way to the right is actually worth 2 to the 0th or 1. I'm going to write the long place value expansion. Hopefully no one did it this way, but this bit, the least significant bit, is worth 2 to the 0 or 1. This 0 bit is worth 2 to the first. Then we have the 1 bit, which is in the 2 to the second place, and then the 1 bit, which is in the 2 to the third. And when you expand all this out, I'm going to do it again from scratch just to make sure. We should have 1, we don't have a 2, we have a 4, and we have an 8. So it's going to be 1 plus 4 plus 8, which is going to be 13 in decimal or base 10. We usually don't put a actual subscript there because we assume that numbers we see that look like decimal numbers, particularly they have the digits between 1 and 9, are in base 10. How many bits are in 3 bytes? Well, the key conversion factor that you need here, well, before we go there, decimal numbers, a single digit is a bit. A byte is a collection of 8 bits. So we need to know that 8 bits is 1 byte. So if you just solve or scale that ratio, do it whatever technique you want. If you have 3 bytes, then you're going to have 24 bits. So this next problem, if you remember, a lot of our actual learning outcomes for the course are associated with matrix and vector computations, which isn't surprising for a computing for engineering class due to the value of linear algebra, both in numerical methods of physics problems, along with the emerging utility of that math in deep learning. So we want to find the value of a subscript 3 comma 2. Remember that by definition, matrices are defined, are a collection, a structured collection of scalars, and we define their structure by their number of rows and by their number of columns. So this, starting in the upper left, has 1, 2, 3 rows, 1, 2, 3 columns. So the element in the third row and the second column is going to be -4 here. So let's write in -4 for that. Computing the transpose of this actual vector. Remember that what we want to do there, the transpose operation, which has a lot of value in numerical methods. Hopefully we'll get a chance to look at coding up some of those numerical methods in a lab, like the least squared solution to a system of equations or something. But anyways, what we want to do here is we can do it on a row or column basis. I'm going to go columns to rows. So I'm going to take the first column in the original matrix, 1, 1, 0. I'm going to make that the first row in my new matrix. So column 1, 1, 0 became row 1, 1, 0. In a similar fashion, column -1, -2, -4 is going to become row -1, -2, -4. And sometimes when you're looking at this, just due to the way I made these numbers, you might start to see a symmetry and be like, oh, that middle number stays the same. Well, yeah, that's going to be a property of a 3 by 3. But if you take column 3, 0, 1, 0, and make it row 3, 0, 1, 0, that should be your actual transpose matrix. And if you want to check whether or not you did it correctly, we went on a column to row basis. You can also go on a row to column basis. So that first row, 1, -1, 0, notice that that is the first column of your transpose matrix. In a similar fashion, row 2, 1, -2, 1 is the second column, and row 3 is the third column of the transpose. So writing this system of equations in matrix vector form, remember that what you want to do there is get all of the variables on one side of the equation and make sure to Actually, you can, if it helps, and I know the majority of you are beyond this in math, but explicitly list the coefficients of any variables that are missing as 0. And you might say, well, Henry, why did you put a 0z in there? Well, in this system, there are equations, particularly equations 2 and 3, that contain the variable z. So I need to, if it's not included in one of my equations, I have to add a 0 coefficient term there. In a similar fashion, equation 2 here, even though you only see a z, if we're going to write it as a system of equations, we need to add in the actual 0 coefficient terms for the variables that are missing. And we want all of our variables on one side, and we want them lined up. So I'm going to move this 4x over to the left. I'm going to add in a 0y term. Don't forget my 2z. And that whole thing is equal to 0. So if I want to actually put this into matrix vector form, I'm going to take, and my coefficient matrix will be, and again, standard form, I have my x, y, z, x, y, z, x, y, z in each of the 3 equations. So I'm just going to extract the coefficients, 1, 1, 0. That is the first equation. So the first row in the coefficient matrix corresponds to the first equation. The second row, 0, 0, 2, corresponds to, or I should say the second equation rather, I wish my printer was working now. That's why I'm having to do this. Corresponds to the actual second row. So 0, 0, 2. And then the third equation, minus 4, 0, 2, corresponds to the third row. So minus 4, 0, 2. Remember that in matrix vector form, you have the actual coefficient matrix multiplied by, and if I go to my insert equation here, for those of you that might be curious how to do this, where we at? I think I was where I wanted to be, but I want to actually insert a 3 by 1 matrix here. And I always tend to do this incorrectly. I think you want to grab, for a funny looking matrix like that, the actual matrix first, and then inside the matrix, put your 3 by 1 column vector. This is the unknown column vector, so it gets each of the unknown variables. And the reason we structure them x, y, and z is because we put the coefficients of x in the first column, coefficients of y in the second column, coefficients of z in the third column. So on the right side of the equation, we have our constant vector here, which will be 3, 5, 0. I know from reading your discussion board post, a lot of you are farther along in your mathematics curriculum, so you know that basically in an actual engineering application, the coefficient matrix corresponds to properties of the actual system itself. And this constant vector over here, you kind of look at that as the forcing function of the system. That's the component of, for those of you that have differential equations, you know there's lots of different ways to decompose the actual solution to a system. You can think about kind of how it decomposes in time, a transient response and a steady state response. You can also think about like kind of a mechanistic approach to decomposing the two responses. Particularly, you could talk about a natural response along with a forced response. So this actual term on the right here is related to the inputs in whatever system you're dealing with. That's your forced response, versus these coefficients are kind of just the coefficient matrix rather, is related to underlying properties of the system that are independent of what the actual input mechanism is. So probably too much math there for you, but in case you were finding this video boring, I wanted to give you a little bit to chew on. So I will break this actual review up into different pieces. So I will see you all in the next video.